Welcome to this module on economic input-out model. In this module, we will go towards the motivation behind using EIO model. Then we will go through the basics of Leontief model, which is one form of input-output model. And then we will do an example of two-sector IO model before we will look at the derivation of n-sector models. So, if you remember process LCA, and we talked about the cutoff errors and the cutoff criteria. So, what is cutoff error? When in process LCA, we are selecting the most important processes, we are missing out on lot of indirect impacts. So, due to limitation in how many processes you can include in your process LCA, cutoff is used, which may lead to large what we call as truncation errors for other associated impacts. Hence, process LCA is known to suffer from missing out some of the critical impact categories or impact due to this truncation error. To overcome this, we use a macroeconomic model. So, before we go there, we will just look at the difference between microeconomics and macroeconomics. In microeconomics, we are studying individual and organization level behavior in allocation of resource and impact, which is very similar to the process LCA. We are looking at specific processes and how they are using resources and emissions and what the impact they are making. But in macroeconomics, what we do, it looks at the structure, behavior and decision of the economy as a whole, and that is the concept behind the development of economic input-output based LCA. So, here instead of looking at one part or one single economic agent for the behavior, we look at how all the agents or how all the system component is actually interacting with each other, and that is what the macroeconomics is. So, that means that macroeconomics is actually a more holistic science or much more holistic in terms of the scope of its analysis, and that is what we need in the LCA, because we do not want to miss some of the important impact which we miss due to the truncation errors. So, that is what the macroeconomic input-output model or the EIO, or in short the IO model is. What it does is that the input-output model arranges economic activities in sectors. Instead of looking at independent processes, it aggregates the processes into sectors which are similar in activity. For example, all the energy production, whether it is coal, oil based or natural gas based or renewable, it will all be aggregated into what we call as the energy sector. Similarly, lot of the metal manufacturing may be aggregated into one, lot of agricultural activities will be put into one. So, each sector in that case is actually composing of activities that are very similar to each other. So, here I have put some of the example. For example, manufacturing of food for consumption will be in the food processing sector. Manufacturing auto parts will be in automobile manufacturing sector, and forest will be in forestry sector. So, you would notice that what happens is that here we are aggregating the sectors, which means we are now ignoring the specific details of the individual actors in that manufacturing part or in that particular category, and we are just aggregating them and looking at the average or the course behavior. So, that is the difference between when we look at more detailed processes versus sector in our analysis, and going forward we will see how we use this model to define our life cycle and all of that. But the main difference here is that we are looking at an aggregated behavior of a certain activity in the economy than fine details of each of those processes. So, what the IO model then does is that it studies the inputs and outputs, which is very similar to our process LCA, where we were looking at a single process and we were thinking of what are the inputs and what are the outputs or the emissions and products that are going. Here, instead of those processes, we are looking at each of the sector from the input output, and it studies the inputs and outputs for each sector, and it can quantify the inputs required from all sectors for output from a particular sector. So, we will see how this model works in a bit, but in summary it is mainly identifying the total impact of economic activities by understanding this structural interaction between different sectors of the economy, and that is what the input output model does. So the input-output model was proposed by Vasily Leontief, who was an economist, and his driving force was his question that was mainly he asked was, how do changes in one economic sector affect other sectors? So if you think about it, this is mainly that what we are also thinking about from life cycle analysis is that how does the whole life cycle interact with each other and how does it impact each other, so that we can calculate the total impact for making of a product or process. His PhD thesis was named as Circular Flows in Economics, and that's what led to the input-output model, and he won Nobel Prize in Economic Sciences in 1973 for his work on IO tables for US economic structure. So now, before we go into more detail of how this economic input-output model works, what are the equations, how do we use it, first the question is that how is economics related to life cycle assessment, or how is the economy related to LCA? So remember process LCA, this is the simple example of, let's say we want to quantify impact of driving a mile in a car. So you can see that you have the life cycle stage of consumption of the fuel by driving a mile. You have energy inputs. You are looking at the upstream processes of oil refinery, and you also have power plant that is providing some of the oil or electricity, and then the coal mining providing the coal for the power plant to actually make electricity. So this is the whole process LCA system, and you can also have some of the indirect inputs which are not shown in this process LCA, as we have talked before that we might be missing some of the processes upstream, but there could be indirect inputs such as manufactured products. There could be food that may be an input to the laborers who are actually working in these manufacturing plants, and henceforth. So you can have lot of these indirect inputs that we have not shown, and it can become very tedious to do and make process LCA very time consuming. So instead, we can actually embed that into this network. So you can see that there can be a chemical manufacturing sector, a water supply, or the transportation sector, and this can actually be part of this whole huge network, which is actually all the economic network in the economy. So we saw that we have these 4 processes in our process LCA, but this small network or the small linear chain that we saw, it is actually connected to all the different activities in the economy. Hence, when you do a process LCA, it is kind of an embedded system in the whole network of the economy, where different sectors are exchanging goods, flows and information, and that is what the connection of LCA with economic models are, or the macroeconomics. So you can have more sectors, and thus what we do is, if we want to do a holistic LCA where we are including the total impact of this process, which we had only 4 processes included, we would want to see a model that can look at the interconnections of all of these sectors. So if we have this network model that tells us that if I am going to drive a mall, what is the impact on chemical sector? So this indirect effect, calculation of that indirect effect is what is needed if we can get a model of this economy. And that is the origin of actually expanding the system boundary beyond the processes to include the whole economy through this macroeconomic input-output model. So let's see what the input-output model is. So we'll first just look at the data structure where we put input-output analysis. And as I said, in an input-output model, so if you go back to this figure, each of these nodes are actually the sectors. So these are our sectors. So this could be sector 1, this can be sector 2, and henceforth. Okay, this can be sector N. And all of these edges are actually directed edges. So you can say that there is a flow of some resource from sector 1 to sector 2. So there are these edges that are showing there is some goods or monetary exchange between sector 1 and sector 2, and that describes the structural relation between 2 sectors. So when we put that information into a tabular format or data for the network representation, we have what we call as processing sector. So all of these are some processing and consuming sectors. On the column, we have all the processing sectors and also the row. So, the way this Z matrix, what we call as the flow matrix, is that Z11 is basically the edge that we just saw, and it is showing that how much is the flow of, let's say, a good or a material from sector 1 to sector 1. So, there might be some flow, let's say electricity production, and it uses its own product electricity for some production, and that is what your Z11 flow is, that there is that flow. Z12 is the product flow from sector 1 to sector 2. So, that is Z12. Similarly, Z1N is from sector 1 to sector N, and your final demand is what we say is going out of the economy. So, which is like you have this whole network where all the products are being manufactured, but your final demand may be something export that is going out of the region, or it might be some consumers that are using that product. So, that is our final demand. So, remember your process LCA network, there also we had final demand which was actually going out of the network for consumption, and in the similar fashion here also we have final demand from each of the sector that is actually going out of the network. Another variable is value added. So, value added is something like the natural resource that is coming out of the economy into that particular economic network for production. So, it could be value added in terms of natural resources, or it could be some value added in terms of labor capital or capital infusement in the economy. And then we calculate total output. Total output is basically the sum of total flows out, or total input is basically the sum of total inputs to the sector 1, and that has to be balanced. So, total input and total output needs to be balanced. That is the requirement of the model. So, we will in our brief see how this requirement is actually set up into equation to calculate the total impact, but this is mainly the introduction of what is the data structure. So, let us quickly review each of the definitions for input output table. If you have not, I would recommend that you draw this table somewhere so that you have an information with you as you are going through the variables. Let us look at the flow. So, Zij is, or Zij is basically flow from ith sector to jth sector, which is also known as intersectoral flow or intermediate flow. So, let us go back to the table. So, Z11, Z12 is mainly the flows that are flowing within the economy from one sector to another sector. So, if you look at the network, these network nodes are actually your intermediate flow or net edges, and if I have some flow that is going out from this sector Fn, that is the final demand. So, here we have Gij or Zij as the flow from ith sector to jth sector is the intersectoral flow. We have Vi, which is the value added to sector I, and this flow is any input to your economic network from outside the system. So, remember that resources are not produced within your system, it is where the economy is interacting with the environmental system, or it is also where you have some of the labor capital which is not being made within the system, it is not an economic product. And then you have final demand, which is basically from any sector I, and this includes that is consumed outside the network, and these are the demands met outside the production sector. And Xi is what we call as total through flow, and in through flow we include both total output and the total inputs in the system. Okay. So, now that we have set up the model, we have set up what are the variables. Now, what we will see a derivation of the equation for this n sector model, so that we can establish the equations that we can use to calculate total impact in the economy to make any product. Okay. So, let us look at the IO model for n sector economy. So, we have seen this data table. So, we will start with this. So, for the n sector economy, we have what we call as, we have the Zij, which is the flow from to jth sector. So what we will do is that for each of the node, the inputs and outputs are balanced. So we'll first write for the input. So we'll have, so the main constraint or the main requirement to set up the IO model flows input and output on a node and your nodes are mainly the sectors in the economy need to be balanced. So it's kind of a requirement which is mainly saying that we cannot create new economic flows in the system. Whatever is coming in a sector in terms of economic flows is what need to go out. So here we can say that our Z11, which is the flow from sector 1 to sector 2, plus Z12 flow from sector 1 to sector 2, which is the output, plus Z13 and henceforth Z1n. Then another thing that's going out is F1, that is the final demand, should be equal to the input. So Z11 plus Z21 and henceforth Zn1 plus V1 should be equal to your X1. So your X1 is total through flow. And that total through flow includes is both the input and output. So if we go back to the tables, so you will see that this X1 is the total output and this is also the total input. If you see an input output table, where your X1 input and X1 output, where the flows in the sector are not balanced, you will immediately know that there is something missing in the model, or there are some erroneous data that has been entered for this model. So let's look at the writing of the equation. So we have written it for sector 1. We can write the same for all the sectors. So we can write it for Z21 So these are our output equations and these are our input equations. So similarly we can write for all n sectors. So we have Zn1 So these are all our equations where we have written the balances for each of the nodes. So these are all, we'll have a set of n equations where n is the number of sectors in the economy. So you can see that what essentially we have done is for each node we have written input is equal to output and that is your total through flow. Okay. Now we will set up the Leontief model by looking at the output side equation. So let's look at the Leontief model. We will look at the output side equation. So here the goal is that we want to know how much is the total output in the economy to support certain amount of final demand. So what we are doing is we are going to relate the intersectoral flows with the final demand and the total output. So when we look at just the flows output is Z11 plus Z12 equal to x1. So that is just the output side, Z21 plus Z22 and so we have our n equations. Okay. So here the first step in getting the Leontief model is defining what we call as direct requirements or direct coefficients. So we have what we call as direct coefficients, and the way these coefficients are defined is they are defined as A ij is equal to Zij divided by xj, which means that, so numerator is flow from ith sector to jth sector, and denominator is the total output in jth sector. So what that means is that this is the coefficient that is actually telling what is the total amount of flow from one sector to ith sector that is required per unit of output from jth sector. And this is what when we get all these values, we set up what we call as direct requirements matrix. So the interpretation of this direct coefficient is what is the direct input that I need to give to other sector to support the output from that particular sector. And the assumption in the IO model, what is made is that for a given period your AIJs are assumed to be constant. So you might have changes in the flow, but these ratios, which is how much is going from one sector to another to support the output from the another sector, is assumed to be constant. This is a big assumption in input output model, but it is valid for a short period of time in the economy because most of these flows are dependent on the technology that is required or pricing, and that does not fluctuate that much in the market on an aggregate or the course level. Hence this assumption is assumed to be valid for short period of time. When you change the time period, of course you need to update this, and this becomes a huge challenge in updating the input output model, and that is an area of research that keeps on ongoing by the agencies that are building this input output model. So now that we have this definition, what we will do is we will replace that Zij's in terms of Aij. So I can write my Z11 can be written as, so let's say we have A11. A11 can be written as Z11 time divided by x1, which means that Z11 will be written as A11 times x1. Similarly, I can write A12 is equal to Z12 by x2, and that means that my Z12 can be written as A12 times x2. So I will do, what we will do is we will replace all the z's in or z's in terms of A's or the coefficients that we have defined and then rearrange the terms to write our final equation. So, let us do that. So, this model then can be written as A11 times x1 plus A12 times x2 Okay. So, now we have these equations. These are algebraic equations that are actually representing the flows in all the n sectors of the economy. So, we can now write it in a matrix format. So, if we have to write it, we can say that we have our A matrix. So, we have A11, A12, So, this is what we call as our direct requirements matrix A. This is the vector of all the through flows x's plus the final demand vector is equal to x. I can simply write Ax plus f is equal to multiply this x matrix by an identity matrix. Then we can take these two together. So, we can have f is equal to I minus a times x, which means that I can calculate x is equal to I minus a inverse times f. This is the famous Leontief model, or what we call as demand driven Leontief model. So, you can see that now we have a very simple linear algebra equation or a matrix equation that you can use to calculate the total impact, and x will be in terms of economic through flows because our model is built on all the economic through flow, and it can also be built on physical model, and we will see a physical input output table later in the course as well. And here we can now calculate the total impact in the economy if we can set the final demand. So, remember your process LCA network structure where you had a final demand, that was your goal of LCA, and here we can do the same thing. Our goal of LCA will tell us how much is the product we want to make from each of the economic sector, and that will help us to set the F. Based on the economic data and flows that we collected, we will be able to get our A matrix based on the definition of the direct coefficients, and then we can calculate our X, what is the total through flow in the economy that is required to support the final demand that we were going to make. Further, we will modify this model to include the emissions and resources data, which we call as the environmentally extended input output model, and that we will learn in the next module. So, this is the basis of actually doing a life cycle impact calculation by using a macroeconomic model. When you have a macroeconomic model available, there is a higher chance of not missing any of the indirect impact because we have everything, the whole economy interconnections captured. So, going back, how is this IO model useful? It can calculate changes in X for each sector based on changes in final demand F for any sector. And then the total impact of any activity in a sector is then related to total output or total input. Thus, it calculates, or it enables us to calculate impact for any amount of change in final demand in the economy, which forms the basis of what we call as the economic input output life cycle assessment. So, let us look at some key points for input output models. The main key point is that most of the sectors represent average production, and the specificity for individual processes is lost, which is the strength in the process LCA. We have linearity assumption because of that direct coefficient matrix being coefficient being fixed. And if 10% more output is needed from a sector, all inputs need to be increased by 10%. Thus, this is the same as we use in the process model, and that is mainly because of that A matrix being a linear combination of the flows. It is cradle to gate. Since we are not going towards the end phase, it is mostly in the economy how the production is being done. So, it is the IO tables are set up to perform. If you use a ready to use IO table, we are mostly performing cradle to gate LCA, which is the impact is only up to the point where product is manufactured and available to use. If you are doing a full LCA, you can include the use phase or end of life separately for the impact to be calculated. Then the IO tables for a particular economy such as US economy or a state economy does not include import unless it is specifically mentioned. Most of the time the imports that are coming in are actually considered being manufactured within the economy, but the actual manufacturing, for example, if let's say you import a wind turbine, the wind turbine may be manufactured in some another country and the economic system for that country would be different. So, if you behave or if you treat the manufacturing of turbine in your own economy for which the IO model is available, your impact would be different. So, we can have overestimation or underestimation if we are including or excluding imports that are being part of your life cycle that you are studying. Circularity is inherent. Most of the time a sector may be using its own product, and since we do not have to track everything, the input output model actually captures everything. We don't have to worry about this indirect effect that also comes in the circularity. So, that's one of the strengths of the input output model. An example of a real IO model is a US economy in 2002 had 426 economic sectors. So, if you looked at this model, it would be a 426 by 426 matrix that shows the A values for each of the sectors. In 1997, there were 498 sectors, so they had changes in the definition. Bureau of Economic Analysis in US provides this model every 5 years, and it uses the North American industry classification. For every country there are different classification system, but there is now a global effort to build what we call as world input output table, and some of those tables are freely available over the internet from the OECDs, and that is where a lot of homogenization of the input output model is happening, so that we can share results among different countries because of the life cycle becoming a life cycle of multiple products are spread across different countries. So, having that world input output model actually helps to capture that impact. With that, we'll move to the next module. In the next module, we will look at the physical interpretation of input output model, and then we will look at some calculations and also the environmentally extended input output model.